Hey Techno Studs, let's talk about using copper to transfer data. We're going to be talking about how copper transmits data, the advantages and disadvantages of using copper as a method to transmit data. We'll talk about cable types, specifically about coax and twisted pair, and then we will wrap things up by talking about some transceivers. Copper is a conductor of electricity, which means that there are a bunch of electrons all up and down a copper wire. And what's happening is that when we apply power to a copper wire, we are either moving the electrons in one direction, in the case of like direct current, or we're moving these electrons back and forth in the case of alternating current. So when we're talking about electricity through a cable, all what we're talking about is these electrons are moving through this cable. And so we can transfer data or transmit data by turning the power on and off to this, or having varying degrees of power. So we can send a signal from one location to the next by either turning the electrons on and off or varying the degree in which these electrons are flowing through this cable. All right, let's talk about some of the advantages of copper. So copper, to make a copper cable is relatively cheap in comparison to like fiber optics. So copper is a cheaper metal, although it's more expensive than some metals, but it's definitely less expensive than making a fiber optics cable. And it is much more reliable than wireless. Wireless tends to be a little finicky, so copper tends to be a very stable connector that's out there. And then it's also relatively easy to install. So copper, where fiber, if you bend it too much, then it can crack. Copper you can bend it around, you can pull it through different locations, and there's some shielding and stuff that can go around it to protect it. So it tends to be a really easy cable to pull through your ceilings and pull through walls and pull through crawl spaces. So that's some of the advantages of copper. Unfortunately, there are some disadvantages to copper. So as these cables, as we run them, the longer they get, the more resistance they put up, and it degrades the signal. This is what we call attenuation. So over time, over distance, that these cables, there's only certain lengths that these cables can go before the signal is unreadable on the other side. So that's one disadvantage, is that the distance of copper is less than what like fiber would be. Another thing is that these lines are susceptible to EMI, or electromagnetic interference. When electrons run through a cable, it lets off these fields. So an electron will, as it goes through this cable, there's these fields that it emits. Now, different cables can interfere with other cables. So for instance, let's say a power line runs across this, or even worse, next to it. The electrons running through that power cable can create these fields that will then interrupt the electrons within our data communication. Another example is that a lot of times we'll run cables next to each other, or even within the cable, there's multiple pairs within each of these cables running next to each other. And so those lines will interfere with each other with this electromagnetic interference. We call that crosstalk. So when one line you'll get bleed over into the next line, that's what we call crosstalk. So that is also a disadvantage of copper lines. So there are ways that we can overcome some of these disadvantages. For instance, attenuation comes in when we go too far of a distance with these cables. And so to combat attenuation, we just make limits on how far we can run these lines. For instance, a copper Ethernet connection is only supposed to be ran about 100 meters. So 100 meters is about what they figure the limit is. You can certainly go past this level of 100 meters, but what happens is it introduces more chances of attenuation, and then the signal will degrade, you'll get retransmits, and the line will not be as clean, or maybe the data has to drop, so we don't have as fast of a connection. So 100 meters is the limit with a lot of our Ethernet cables. Another thing that we could do is we could create a shielding around this cable. So if we have a shielding, some sort of conductor that goes around it, and we ground that out, so we put that to ground, then what we can do is we can shield this data, or the electrons that are going through this, from outside interference. So putting shielding around these cables is one way that we can reduce the effects of EMI. Another thing that we've found is as we will take these cables and we will twist them together and create a twisted pair. And when we twist those pairs together, then we can reduce the amount of crosstalk that happens. So we're going to get much more in depth into twisted pair and what it looks like. But just know that that's another method that we can reduce the amount of crosstalk on these lines and take away some of those disadvantages that we have with copper cable. There's a lot of different copper cables that are out there. A couple of the categories that we will be talking about is Ethernet cables and twisted pair. So we're going to get much more in depth into twisted pair and Ethernet cables. But there's also coaxial. And so a lot of you probably have some sort of cable that's running into your home that's transferring data. And that cable is, a lot of times, it's coaxial cable that's running into those homes. So we'll talk about these two different types. All right, let's take a look at coaxial cable and what makes up a coaxial cable. So first of all, this center part right here is the conductor. So that's where the data is actually being transferred across. So that's the center conductor. Then we have a dielectric around the outside here. That's an insulator. It insulates, it makes sure that no electricity is flowing between that center conductor and the outside foil. So then we have the outside foil here. That's a foil shield that protects it from some of the EMI that will be around this device. That's what's protecting the data, so it can the data can be cleaner as it comes through that center conductor. And then we've got the braided foil, a braided shield around the outside. So we've got kind of two shielding components here. And then finally, we've got the jacket along the outside, so that none of these conductors are exposed to it. So that's coaxial cable right there. There are a lot of different type of coaxial cables out there, and we don't need to know all of the differences. Just know that, like, the size of the conductor, and there's some other variables in here that are going to change, that are going to determine which standard is out there, and they're all going to have their pros and their cons. I'm not going to name them all because, once again, the nuances between those the differences are really not that important. Just know that one of the things that defines these out there is the radio guide, or what is the RG, will define what are the different for each one of these types, what are the characteristics of those. So RG6 is one of those. RG11, RG59 might be some of those that you still see out there. A lot of your cables, though, you're going to be probably working a lot more with Ethernet cables within your networks, unless you're working for some of those, some of the big ISPs that have these cables that are running there. And then the other thing is occasionally we'll see twin-X cable out there, or twin-axial cable out there, and that's where you have multiple conductors in the middle, or two conductors in the middle. So it's the same type of cable with the shielding on the outside, but this inside part will have two different strands to it, and we'll have two different conductors going in there for the data side of it. Right, there's also lots of different type of connectors out there as well. We don't need to know all of the different type of connectors, but two that I'm going to mention is the F-type of connector and the BNC type. The F-type of connector are the ones that have threads on the inside, so you can see threads that are on here right now. And those are the ones that you're going to put into the equipment, and you're going to be turning quite a few times to get it fully screwed on tight. So that's the F-type. Then you have the BNC type of connectors, and what they do is on the other end of it, it will slide onto there, and there'll be probably about a quarter of a turn or a third of a turn to actually lock it into place. And so there's the hole right there, and that and then a slot right here, and so that slot will go over kind of a part that sticks out a bit. It'll slide on. You'll put a little quarter of a turn in there, and they'll snap into place into where this little hole is right there. So that's the type you'll push on and do a little quarter of a turn to make it stick. So F-type connectors and BNC are two of the most common type of connectors that are out there. So you're going to see a lot of twisted pair that's out there. So let's talk about some of the components of twisted pair and get really familiar with twisted pair. So first of all, it does have a jacket just like coaxial does. We see that it has a shielding that goes around it, but not all twisted pair has shielding. You have essentially two different categories. You've got shielded twisted pair, or STP, and you've got unshielded twisted pair, or UTP. The more common out of the two actually is UTP. So we see a shielding on this particular example, but that doesn't necessarily mean that you have that it's on all cables. If you have the shielding, it also has this extra little cable that runs through it. It's a conductor. It's not insulated at all. It's just running along that shielding, and it helps ground that out. So that's actually what you would run out to your rack or something else that's grounded, and you would ground it out, so that way that's what would protect these conductors, so that way you have less interference. We also see, then one other thing that you'll see also is every once in a while you'll see, or a lot of the cables will have this ripcord. It's an extra little thread that comes out of the jacket. And what it's used for is to take off a big chunk of that jacket, meaning that you can grab a hold of that and pull on it, and it will slice down the jacket lengthwise, and then you can peel that back and cut it off. So it's a quick way, an easy way to take the jacket off of a large section of this cable. So we've got that. The other thing that we see here is we've got this center little core to this. Not all of your twisted pair is going to have that either. So the core right there it looks like a little plus sign inside of this cable, and it's separating out our 4 pairs. We can see our 4 pairs here. So that will be inside of some of your cables, but not necessarily all of your cables. Okay, so let's get into the pairs. As we see right here, we actually have 8 different conductors. So in the middle of each one of these lines is a conductor. And we break those conductors into pairs. So they're grouped into 4 pairs. So we have 4 pairs. Now, each one of those pairs, one of them is essentially a ground for the pair, and then one actually transfers the data of the pair. So, and then we can see that they're also color-coded. So each one of these has a jacket in itself, or an insulator in itself, so it's not all grounding itself out against the other ones. So they have these insulators to it. The conductor is in the middle. We see here that this is a white cable with a yellow stripe that's running down it, and with an orange stripe that's running down it, and this is a orange cable. So this is the orange pair, and it consists of a white orange and an orange. And then the green, we have a white green and a green, and the blue, we have a white blue and a blue, and the brown, we have a white brown and a brown. So each of the conductors, that's how we identify which one is the data and which one is the ground, and which ones are paired together. So those are the different pairs of this, and it's going to transfer the data. So we have 4 different pairs on this line. Typically with twisted pair, we're not running it directly from device to device where we have to go and wire these things up. We usually have connectors on the end of these, and the connectors are usually the same connector. There are a lot of different type of connectors that we can put on the end of twisted pair, but the one that we're most concerned with, and you'll see on the majority of the equipment out there, is the RJ45. So this is a registered jack 45. And so it defines what the dimensions of this end is and the conductors and the pinouts of these conductors. So the RJ45 is the connector here at the end, and we are going to learn more about the RJ45 in future videos. Okay, let's talk about transceivers. Transceivers are not just specific to copper, but it is also fiber as well. So, transceivers, what these are SFPs, or small form factor pluggable. That's what SFP stands for. And some of these, as you can see, are fiber. These ones that I'm circling right now are fiber. And then this is an example of a copper. What these are is they are small little units that will slide into your switch to give it additional functionality. So you may have a switch that just has regular RJ45 jacks for copper, and then off to the side there might be 4 of these little slots that these will slide into to give it extra functionality. Or maybe your switch that's all it has is just all these slots, and to give it any functionality at all, you have to slide these different transceivers in there to give them the functionality. And you either slide a fiber one into there, or you slide one that's RJ45, or I've even seen copper cables that have these SFPs on the end of them that are fixed to that cable, and then you're just going from device to device with that. If you like my videos, please hit that like button because it really helps me out. There are different standards with these transceivers. So there's SFP, there's SFP plus, there is Q SFP. The Q stands for quad, so quad, small form factor pluggable, and there's QSFP plus. So there's different standards out there. The biggest thing that you need to be concerned with is that these can slide into your switch to give it extra functionality, and they'll have a copper end to it, or it'll be a fiber, or the cable itself will have these on the ends of it, and you'd slide those into your 2 devices that have these type of connectors in it, and you'd slide in there for that. And once again, generally these are much faster connections than your straight RJ45 connectors that you slide into there. All right, we talked about how copper cable transmit data, and that is those electrons, we can adjust the flow of electrons to interpret different sets of data there. We talked about some of the advantages and disadvantages. Really, when it boils down to is there's a lot of advantages over copper, and we found ways to get over some of the disadvantages of copper cable. And so it is one of the most prevalent forms of transmitting data that's out there. We talked about the different type of cable types, whether it be coaxial or twisted pair, and some of the connectors that are associated with both of those, and some of the standards that are used with both of those. And then we finished it up with talking about different transceivers, and we talked about it not just from the copper sense, but also from the optical fiber sense. So here are some of the information about copper cables, and we're going to get, in the next videos, we're going to get even deeper into twisted pair, because that is going to be the one that you're going to most prevalently be working with out there.